We present a unit-based discriminator for generative adversarial networks. Our work introduces a new discriminator architecture for improved image generation with GANs. Most images generated with GANs only look realistic at the first glance. Often, we see that a lot of details in the images are inconsistent, or that all the right parts are there, but the spatial arrangement is incorrect. We often see structures that are only partially correct, yet the generator still managed to convince the discriminator that the image is real. Therefore, in this work, we introduce a new discriminator architecture that additionally evaluates different image regions independently. In particular, the new discriminator segments the image into real and fake parts, giving a stronger error signal for the abnormal image regions. This way, the discriminator is not only harder to fool, but also gives a richer and more detailed training signal to the generator. Therefore, we propose to let the discriminator take the structure of a typical semantic segmentation network. In particular, the discriminator should have an encoder-decoder structure. This means the GAN loss is now calculated per pixel on the decoder output. An example of the decoder output is shown on the right. The dark areas are classified as fake by the discriminator, and bright areas are classified as real. Potentially, such a per pixel discriminator may come with the downside of completely neglecting the global composition of the image. This can be addressed in two ways. First, we calculate the loss for both the encoder and decoder outputs. This way, we have a loss for local and for global realism. Second, if you add skip connections between the encoder and decoder, as well as in the CNN blocks, then the local loss is not entirely local, but also takes information from all scales into account. That's why we propose a unit structure, which is conceptually simple and very popular for semantic segmentation. As you can see in the visualization on the right, the image is basically segmented into real and fake parts. Let's have a closer look at the exact architecture that we use in our experiments in order to get a better idea of how our proposed unit discriminator works. The left half of this figure corresponds to the original GAN discriminator that we took as a baseline for our experiments, consisting of 6 ResNet blocks. We then add a decoder, which is made of the same ResNet blocks, but the input channel sizes are doubled thanks to the skip connections between encoder and decoder. We continue to compute the original GAN loss at the encoder output. Note that normally a unit does not have an encoder loss. For the decoder loss, the loss is computed per pixel. Then we average the loss over all pixels and add them to the encoder loss. In our experiments, we choose the non-saturating GAN loss. Now the question arises, do the encoder and decoder agree or disagree when they predict the probability of an image being real or fake? To address the question, how much encoder and decoder disagree, we here plot the encoder and decoder predictions for a training batch of generated images. On the x-axis, you see the encoder predictions, which range between 0 for completely fake and 1 for completely real. Similarly, the y-axis shows the average per pixel prediction of the decoder. Every blue point corresponds to an image in the batch. As you can see, the encoder and decoder have a fair amount of disagreement. The disagreement explains the performance gains, because the generator now has to satisfy different critics. This also means the discriminator is harder to convince that the fake image is real. The fact that the unit discriminator is harder to convince that an image is either completely real or fake is also reflected in the training loss curves. On the left, you see the generator and discriminator loss of our baseline, and on the right, you see the losses after we modified the discriminator into a unit shape. A problem that we see in GANs is that if the discriminator loss drops too low, it does not produce useful gradients for the generator anymore. The discriminator loss is low when the discriminator can almost perfectly distinguish real and fake images. This is less likely to happen in the unit discriminator because it would require the encoder loss as well as the individual decoder losses to agree with each other. Hence, in the right plot, you see that the unit discriminator loss drops more slowly and provides useful gradients throughout training, which result in better image quality. The fact that our discriminator computes two-dimensional predictions allows for interesting new regularization schemes. Here, we are interested in structure awareness. When the unit decoder classifies local patches into real or fake, it should preferably pay attention to the semantic content and structural properties, such as objects having the right shape and having the right parts sit in the right places. For that, we may encourage the decoder predictions to be equivariant under image transformations that change whether an image is real or fake globally, but not locally. An example of such a transformation is CutMix, which samples a binary mask to cut and mix two images together. In our case, we cut and mix a real and a fake image. In effect, the new whole image belongs to neither the real or fake class, whereas the class identity of local image patches that are classified by the decoder has not changed. Given a decoder function D and the CutMix transformation T, equivariance under the CutMix transformation means that the order in which D and T are applied should not matter. Hence, we can enforce equivariance through a consistency loss. The consistency loss minimizes the L2 distance between the decoder prediction of the CutMix image on one side and the CutMix of the decoder prediction of the two individual images on the other side. Apart from the consistency regularization, CutMix can also be used for data augmentation. In the original CutMix implementation for GANs, the target value for the discriminator is the fraction of the white pixels in the binary mask. However, in the unit discriminator, we can use the binary mask to directly provide the ground truth targets for the binary cross entropy per pixel losses of the decoder. In other words, the decoder has to predict 0 for the fake regions and 1 for the real region, this time within the same image. In contrast to the original CutMix, we do not use soft targets for the encoder, but always use fake as the target, as otherwise the generator can learn to generate artificial CutMix images. The data augmentation and the consistency loss are two separate regularization schemes that can be implemented side by side and reuse the same mixed images. Next, we will present the experimental results. The datasets we use for our experiments are the following. The CelebA and FFHQ datasets of faces are used for unconditional image synthesis on resolution 128 and 256. For class conditional image synthesis on resolution 128, we make use of the Coco Animals dataset, containing 10 animal classes. We use Coco Animals and FFHQ to assess the effect of our proposed changes. For our experiments, we take the state-of-the-art BigGAN as baseline. We turn the discriminator of BigGAN into a unit by adding the decoder and the skip connections. We did not change any of the learning parameters. Image generation quality is measured by the FID score, where lower means better. Here we see that the two biggest improvements come from the unit architecture as well as the consistency regularization. We achieved the best outcome when combining CutMix augmentation and consistency regularization. Our method improves on all three datasets over the state-of-the-art baselines. On the right, we show generated samples produced by our method. The upper row shows smooth latent space interpolation between generated faces, while the lower row shows different animal pictures that we synthesized in the class conditional setting. Here we see more images generated with our method. In summary, we propose the idea of using a segmentation architecture as discriminator. In particular, we propose the unit discriminator, building on top of BigGAN. The unit discriminator computes the GAN loss per pixel and thereby gives region-specific error signals that improve the generated images throughout training. Further, the 2D discriminator output space offers interesting new possibilities for regularization. As such, in this work, we have demonstrated the effectiveness of a new CutMix-based consistency regularization. Finally, we demonstrate the improvement over the state-of-the-art BigGAN baseline on 3 datasets. Thank you very much for your attention. For more details, have a look at our paper.